And thank you, and please notice that we are at UCL because I had another technical problem. I could not connect here to change the place. That's the seminar I've given last Monday, so sorry for that. So I'll be talking about inertial instability, and anyone, or almost anyone in this audience knows what's that from the textbooks, but hopefully you will learn something new from this talk. And basically inertial instability, I will treat it in the context of general jet stability or instability of jets, and here are people who are interested in that. And you should also put it in some relation with Jeff Vallee's talk earlier in this program. So perhaps you'll see the relation later on. So just a general reminder before I start with our motivations. By the way, I didn't say this, it is on the last transparency, but this work is done in collaboration mostly with Bruno Ripstein, who was my former doctoral student. Now he's postdoc in Frankfurt, and Anne-Sophie Tissier, also a student, and Rivar Plugonven, they will concern the primitive equations. And basically I come back to my motivations and to the general context of jet instabilities, and the instabilities which are known or expected for jets are shortwave Kelvin-Helmholtz shear instabilities, long-wave barotropic instability, long-wave baroclinic instability, and symmetric inertial instability, because what you find in textbooks is just the symmetric form of this inertial instability, and whole of my talk will be about the asymmetric realization of the same instability. And the interpretation, the loose interpretation of the instabilities, I mean, that's not loose interpretation of the origin of the waves which are driving these instabilities. You explain normal instabilities through phase logging and resonance of the linear waves which are propagating in the background flow. And the possible types of propagating waves are Poincare or inertial gravity waves, and baroclinic and barotropic Rossby waves. And those guys are propagating due to the elasticity of the isodensity or isentropic surfaces. And this one, loosely speaking, now I'm there, is due to elasticity of the iso-PV surfaces. You need the gradients of PV for propagation of Rossby waves. Now the interesting twist is, and I'll be talking about that, on the equator you have much more waves, and we've seen them in Junichi talk yesterday. This offers perhaps, and we'll see that this really is the case, some more possibilities. So how you interpret the instabilities in this way? The standard instabilities are the KH barotropic and baroclinic, as I told you, and KH instability is the resonance between two Poincare waves. The barotropic and baroclinic instabilities are due to resonances between pairs of Rossby waves, and normally, usually in textbooks, you look at them in the geostrophic limit, the limit of small Rossby numbers. From this point of view, the inertial instability is non-standard. That's the first thing you will not find probably in textbooks. Normally, inertial instability is explained in Lagrangian terms, and this is about the wrong sign of the gradient of the geostrophic momentum, and the flow tends to minimize energy, and particles are ejected from their places in order to do that. That's the explanation you'll find, for instance, in Holton's book. But I'll propose you another one, again in terms of waves, but this instability cannot be explained in terms of propagating waves, but only in terms of trapped waves. And these trapped waves, it happens, I'll show you shortly how it works, may have a negative eigensquare frequency, which means, of course, instability. Usually when you are solving for the eigenmodes and eigenvalues of frequency, here you find some imaginary values. Here, in this case, you are solving, I'll show you that, in terms of squares of frequency, and you may find negative solutions. This instability is essentially ageostrophic. It needs Rossby number of the order 1, because again the standard explanation is for the northern hemisphere that you need to have a negative potential vorticity. A negative potential vorticity means that relative vorticity is stronger and of the opposite side the planetary vorticity. So that's it. And again, in the textbooks, it is considered in this symmetric manifestation, meaning that if you have a jet, let's talk about jets, you are perfectly symmetric with respect to translation along the jet, and this instability is realized in this configuration. That's very important to say that although this instability can be realized in the barotropic flow, non-stratified barotropic flow, you need vertical space in order for this instability to be realized. In 2 dimensions it doesn't exist, okay, and you need vertical space. Again, on this stage I can show it with hands. It is well known that inertial instability produces overturning motions, and you need vertical space to have them. We'll see how it works more concretely in what follows. Okay, now I'm coming to the motivations. So the questions are the following, which you can ask. First of all, how the departures of this translational symmetry affect the inertial instability. This question is long-standing, and the first, to my knowledge, was Tim Dunkerton, who asked it in the context of the tropical stratosphere. But the answer, definite answer, again, as to my knowledge, is not known. There are other works. I cannot cite everyone here. The second question is, this instability is standing apart. So what is its relation to the standard instabilities, if any? Now, the related question is, what is the essentially ageostrophic portion of the baroclinic instability? Because again, everywhere in textbooks, articles, etc., you see it in geostrophic way. Now, how inertial instability saturation linearly, there is some work on that, but mostly in the symmetric context. And again, what's the difference with respect to the baroclinic and barotropic instability saturation? And finally, I already mentioned that inertial instability is endemic on the equator, because it's very easy to change the sign of potential vorticity on the equator. What are the differences between mid-latitude, because it also exists, although in mid-latitudes inertial instability is usually considered, for practical reasons, in the moist context. I will be completely dry in this talk. But still this inertial instability exists on the F-plane. So what's the difference between F-plane and equatorial beta plane, practically speaking? So now how we'll approach all this. So our strategy will consist in 2 parts. The first part is detailed stability analysis in a wide range of Rossby numbers. Of course, we will be concentrating on the long wave sector of the instabilities, because as you understood, we want to be close to this symmetric inertial instability regime. And then we use the information obtained from this linear stability analysis in order to initialize the numerical simulations. I've been repeatedly attacked by people in the audience when I was using the word direct numerical simulation for that, because people have very strong opinions on what is direct numerical simulation, what is not. So I'm saying numerical simulations to avoid any confusion. Okay, so what will be the models? We'll start with the simplest 2-layer rotating shallow water model, because as I said, in 1-layer rotating shallow water, which is basically 2-dimensional, there is no inertial instability. We'll be treating it on the F and the equatorial beta planes. And then we'll pass to the primitive equations, continuously stratified case, but for the moment we have the results only for the F plane and not for the equatorial beta plane. So the method for the first part is pseudospectral collocation method, meaning that it is just straightforward discretization with some tricks, Chebyshev points, Chebyshev differentiation matrix, etc. And numerical simulations will be our finite volume well-balanced code, which we developed with Francois Bouchou for rotating shallow water in 2 layers, which copes with the important hyperbolicity loss problem in this model. And for the primitive equation, we'll be using the Worf model, which is not maybe the most precise, but the advantage is that it is a community model that everyone can repeat the simulations. And it is online, etc.
You say one thing about dealing with hyperbolicity loss.
Yes, I will come to that in detail later. So we'll start with I'll explain all the notions and how it works on this example of 2-layer rotating shallow water on the F-plane. Here are the equations of the model. These are momentum equations for 2 components in each layer, 1 and 2, 1 on top of 2, if I'm not mistaken, and mass balance in each layer. This is F-plane, so the Coriolis parameter is constant. So here it is, and this is the stratification parameter, which gives you baroclinicity, together with the height ratio, because you can vary also the ratio of heights of the layers in this model. Okay, now our example on the F-plane will be the barotropic Bickley jet, again, a standard configuration in stability studies. And you can, so the starting point is here. We want really the barotropic jet by the reason that it is easier to find inertial instability in it. You can also do it with any configuration, but here I repeat, it is more it is easier to find the inertial instability. It is more pronounced. So we start with this velocity profile, which is the same in both layers, and we adjust the thicknesses of the layers in order to have the geostrophic balance for this, because for any jet in this model, for any jet which is in one dimension, it is a solution if it is in geostrophic balance. Okay, here are the parameters, but we will not have time to dwell into the dependence on other parameters. The important ones are Burger number, Rossby number, which is defined in terms of the peak velocity of the jet, the aspect ratio, the ratio of heights, and this R parameter. Okay, so I'll begin. This is the configuration we're talking about. This is the velocity profile, the same in both layers. You see dotted one layer and solid another layer, the corresponding height profiles, and here is potential vorticity, and I'm giving here an example where potential vorticity is negative. This is when this anticyclonic shear of the jet is strong enough. Okay, and this is a condition, again, I didn't explain that, I will do in a moment, of the realization of the inertial instability. You see that for the jet with the Rossby number, which is, as I remember, 2 here, you have already this negative potential vorticity in both layers. Okay, this is just to keep in mind what the configuration is. So the jet is in y direction. On the F-plane it is the same, zonal or meridional, because it is invariant with respect to rotations, and the x is the cross-jet direction. Okay, so now I start with a symmetric configuration in order to explain you the ideas, and this analysis may be done almost by hand because it is simpler. So I remove all dependence on the long jet coordinate y. So I treat the perturbation to the initial height and velocity profiles, as you see. And by standard manipulations, I would say in this audience some massage, you can reduce the whole thing to 2 equations for 2 cross-jet velocities. And this, in fact, is a pair of coupled Schrödinger equations, if I may use this analogy. Okay, so you see in this context that the absolute vorticity of the jet, which is here, okay, and which is a proxy for potential vorticity because you just divide by the thickness to get a potential vorticity in each layer, plays the role of potential in the Schrödinger equation. And this fellow, you see what I already promised, that you have an eigen problem for squares of eigenvalues. Okay, so it is useful to introduce baroclinic and barotropic components of velocity. Baroclinic is, as usual, just a difference, just a shear, and barotropic is defined this way without r. There is a choice, but I just defined it geometrically in terms of both. And then you have this integral estimate for the eigenvalue squared, for eigenfrequency squared, which is given by these integrals. And you see that if the barotropic component of velocity, to be checked a posteriori, is negligible, okay, all is defined by these two terms. This fellow is positive definite, r is less than 1 for static stability reasons, okay. This term is positive definite, but this one not. And if the anticyclonic, it's negative, shear is strong enough, this fellow overcomes this one and even this one, and you may have negative frequency squared. Of course, this estimate is obtained for the trapped modes with boundary conditions at infinity, with vanishing boundary conditions on infinity, because there are some integrations but here. So this is an interpretation I promised of the inertial instability. This is inertial instability if this happens, okay? And a posteriori you check that it's really baroclinic in this sense, because this changes nothing, the presence of this term. And you see how it can happen, and it does happen. It does happen. And this is inertial instability in terms of trapped waves. Okay, so we understood that. And in this simplest symmetric case, you can simply solve for eigen modes. You have two rows, real and imaginary parts, because eigen problem is a linear problem, so you normally have linear combinations as solutions, so you may look only on their upper row. This is the geopotential anomaly, again, upper layer, lower layer, solid and dashed. This is across jet velocity, and this is along jet velocity perturbation. And what is important here is you see that in both layers it is really trapped, because it is vanishing very fast towards infinity, and it is concentrated on the anticyclonic. I remind you that anticyclonic part of the jet is here on your right from 0. It is really trapped in this potential well, which is formed by the anticyclonic shear. Okay, that's an interpretation. Now, that's the full two-dimensional stability diagram. Of course, I'm sparing you all the details. This is just a result. And this is small Rossby number, not that small, but still small, 0.5. The results here and below will be presented in a form of stability diagrams, meaning the real part of the eigenvalue normalized by k, which gives you a phase velocity of the perturbation along the jet, and imaginary part of the eigenfrequency, meaning the growth rate.
Okay. Those modes would have a critical level if they were not growing.
Who has critical level? Sorry.
I mean, it's because they have a positive growth rate that they don't have a critical. I mean, they don't have a critical level?
The trapped modes? No.
Yes. But I mean, it's a range of.
These fellows, yes, because for these fellows, trapped modes are symmetric. It's just oscillations in this direction. You can.
I'm asking if the phase speed is in the range of the flow velocity.
The phase speed is not in the range of flow velocity.
It's faster.
Here, at least here. But if there are critical levels, we can treat them. I mean, it's not a problem. Just change the resolution and see the numerical convergence. So this is the full stability diagram. Okay, so we can discuss the details later. But critical levels or not. Some of them will have critical levels, but this is not. I repeat, this is not a big deal. This will be perhaps okay. Anyway, let me continue. So what you see here is the phase velocity, which is not that interesting. This is the growth rate, and you see first three modes, and I am concentrating on the low end part of the spectrum for small k. There is some stuff here which is less important and filtered out. So, of course, as usual, what are we mostly interested in is the highest growth rates. And here are the three highest growth rates for three modes. And what you expect for small Rossby numbers, which is basically a geostrophic regime for this jet, is that the barotropic instability, we have a barotropic jet, is the strongest. The baroclinic instability is the second. That's the general wisdom. And this is confirmed by this calculation because, in fact, this is a benchmark because what we have here, this is the cross-section at some point of the most unstable mode. And again, this real, this imaginary part, you can see, look only on the upper row, and you see that basically all fields are following each other, so they're basically barotropic. So this is the same in both layers. Okay, it's no surprise. This is the highest growing mode. It's photo taken from above. This upper layer, lower layer. This geopotential perturbation or geostrophic stream function plus velocity field with arrows. And again, this butterfly structure is well known for the barotropic instabilities. And again, you see that basically it is the same in both layers. So confirming again that this is standard barotropic instability of this jet in this regime. So no surprise. The second instability is clearly baroclinic. Again, this is this cross section. Okay, and you see that there is a phase shift between the two layers, and it is confirmed by the upper view of two-dimensional view of this instability. You see that these phases are basically opposite here, although you still preserve this butterfly structure. Okay, just for curiosity, the third curve on the graph corresponds to the dipolar barotropic mode. You see dipolar, I will be using monopolar dipolar in terms of cross-jet structure. You see here positive, negative, and in the previous, the most unstable mode, you've seen only one sign of geopotential anomaly. Okay, so I repeat, this is a benchmark. This is what is expected for this barotropic jet. But now, the interesting things happen when you increase Rossby number. And then you increase Rossby number, and here it is really exaggerated to show you the beauty of the stuff. So it is Rossby number 5. Okay, other parameters are here. Yeah, I didn't say that, again, the standard wisdom and what you see again in the textbooks is that the growth rate curve starts from 0. When k goes to 0, you have 0. Okay, this is standard curve for the baroclinic instability. Look at, or barotropic instability, Pedlowski book or whatever. So what happens here when you increase the Rossby number? At some Rossby number, you have a bifurcation, and this phenomena appears. You see that there is a non-zero growth rate at 0k, and this is symmetric instability. This is symmetric with respect to rotation. You have infinite wavelength. Okay?
Vladimir,
Yeah?
you're not thinking of 0 as the equator here, right? Because you're on the
0 as critical. Critical in what sense?
You're not thinking of 0 as the equator.
No, it is on the F plane. It's all on the F plane. I'll be talking about equator later on. It's all on the F plane. But there are several important things. Only two higher, most unstable modes are represented here. And there are two important points. First, this bifurcation appears at Rossby in this context more than one. I don't remember exactly the figure. And here you see that it is really here. This is what you would say is the symmetric instability. It's symmetric. I don't know whether it is inertial or not yet. But still, the maximum of the growth rate is out of 0. Is non-symmetric. And another important point is that there is a second unstable mode, and there is a crossing. So the instability swap at some wave number. Okay, so there are many interesting things happening with increasing Rossby number. So now I'm showing you the cross point. The structure. This complicated topology. So the structure of the most unstable mode, of course, the most unstable is the most important, because if you perturb with the right nose, sorry?
Probably not important, but you only get 2 modes here.
No, I show only two modes. There are a lot of them. I show two dominant modes because there's a lot of mass with much less Rossby, much less growth rate. Sorry, and if I move here, there will appear the shear instabilities with higher growth rates. But I am interested in the long wave sector, as I said. Yeah.
So for which is there a critical Rossby number for which this
Yes.
this change?
Yes. I don't remember here the figure. I remember it for equator, but it is between 1 and 2 someplace.
So reasonable.
Yeah. Yeah. It is not fantastic. Here I exaggerate and I show 5. Okay, because here it is clearer. But so now I'm showing the cross stuff, the structure of the mode with the cross. And what you see here is again the same cross section as I showed for the symmetric situation. And you see the striking resemblance, if you remember, with the mode we found in this symmetric analysis. Okay, and again you see that although this mode is modulated along the flow, it is concentrated on the anticyclonic part of the jet. Clearly, it is trapped. Okay. And this is the unstable mode. So this is the asymmetric inertial instability. Here is its photo. It is clearly baroclinic because this upper layer, lower layer, there's a difference. It is still, you see the maximum, the maximum of the jet is at 0, and this mode is clearly concentrated on the maximum of the anticyclonic shear, so this potential well, which is created by the potential vorticity anomaly, and it has a dipole across jet structure, unlike the standard barotropic or baroclinic instabilities. Okay, and this is the dominant mode. Now, the second unstable mode is barotropic, as you see. The two curves for each variable are following each other, either for a real or imaginary part. And its structure, although also dipolar, is the same in 2 layers. So, the interesting conclusion, intermediate conclusion, is that at high Rossby numbers you have baroclinic instability, which is stronger than the barotropic one, which is somewhat unusual. And second, there is a dipole across jet mode and not monopolar, as we're accustomed to. Okay. Now, okay, I'll skip the numerical simulations of the. Yeah, you asked the question, so I will not skip that. The numerical simulations of the nonlinear evolution are done with this 2-layer shallow water code. And this is the evolution of the thickness in both layers. That's initial stages. That's vertical shear and potential vorticity in each layer. Okay, so you see these gray zones, and these are zones of high shear, and the gray is enhanced dissipation because we don't have explicit dissipation in the model, but we have numerical dissipation due to the slope limiters. And at the same time, these are the zones of the hyperbolicity loss. And I should remind you, or I should tell you, for those who don't know, that in the 2-layer shallow water model, the criterion of hyperbolicity loss, which is a big problem in numerical simulations of this system, coincides precisely with the criterion of the Kelvin-Helmholtz instability. Yes?
What it would mean? A very naive question, hyperbolicity. What is hyperbolicity?
The shallow water system is hyperbolic in a sense that you can solve it by the characteristic method. Okay, it's quasi-linear system. Okay, and it's quasi-linear system, and if you write it in a sort of a matrix form, like sorry, if you write it in the form plus a.
You should not ask questions. Got the most powerful Pauli effect. I'm pretty sure. Destroy last existing working technology.
It's a memorable show, so this is
Pocket.
Your pocket. That's where
you
you
can
can
write it
your
down.
way.
Because I can disappear with it. Okay. Do you hear me like this? So if you write in this way, so schematically, where U is a vector or whatever. So this is the general form of the quasi-linear system, and you can see that, you could see that our two-layer model is of this form. But the standard way of doing it by the characteristic method is to find the left eigenvalues of this matrix and to change variables and to go along the characteristic directions. But you can do it only if this matrix has all eigenvalues different and real. And if by some misfortune they are complex, you have a ellipticity region. Okay, so you cannot, your information cannot go through. There are zones where you change type, your characteristics stops there. You cannot go through because numerically, I mean, even not numerically, qualitatively, it is an easiest way to understand what's going on in the system. You go along the characteristics and you transport information and all properties along the characteristics. So it's a drastic thing, which may happen, it is well known, but physically, I mean, forget everything, forget mathematics, the mathematicians will excuse me. Physically, it means that you have a very strong shear and you have the Kelvin-Hubble instability acting. Of course, we don't resolve Kelvin-Hubble instability in this two-layer model, but we have a proxy for it, which is this hyperbolistic loss. Because the criterion, I repeat, is exactly the same. If you take the standard KH instability criterion and apply it to the shallow water context, okay, you'll get exactly the hyperbolistic loss condition. You had a question or no?
I just had an idea. So.
That's good. But you should look at this as a good news, in fact, because the problems with all previously existing almost all numerical models for the system with loss of hyperbolicity, they just stopped at this moment because the hyperbolicity loss regions started to propagate and to occupy more and more space, etc. Here they remain well localized. Okay, so
how the front of propagation looks like in hyperbolic cases? You have a jump or infinite differential function or what? The asymptotic of the function, how the front of propagation looks like in hyperbolic case?
Here you don't see the front of propagation of decision. You see only the zone where there is no hyperbolicity, where your characteristic can penetrate. And this is the zone, I repeat, where the shear between the layers, the absolute velocity difference between the layers, whatever the direction, is greater than some threshold. Okay, so here is the late stages of nonlinear evolution instead of thickness. What I want to show you, there are some, physically speaking, small-scale vortex structure which appear, and clearly the emission of inertial gravity waves. So this instability is effective source of inertial gravity waves. Here is the potential vorticity again, which confirms the existence of small-scale structures. And I'll not stay long with this because I'm running out of time. And this is hyperbolicity loss stuff. And you see that in this simulation, the hyperbolicity, once it's lost, it's recovered very slowly because basically it is dissipation which cures everything up. But as I said, you can believe it because these hyperbolicities also remain well localized and not propagating and not polluting the whole domain. Now, the interesting thing is the energetics of the saturation, and everyone remember from the textbooks that standard barotrainic instability is the transformation of potential energy of the perturbation into the kinetic energy, and this is exactly inverse which happens. So here is the kinetic energy, here is potential energy, this is the total energy which decreases of course due to this numerical dissipation, and you see that at the early stages, and we'll see this in a more flagrant way later on, the potential energy is increasing with respect to kinetic energy. So it's this inverse transfer of energy, which is rather characteristic for ageostrophic instability. And another thing which is more or less obvious is that the ageostrophic motions, which are not balanced, are intensified. And we just take a simple measure of the ageostrophic motion, the norm of divergence, and you see that in time, the baroclinic ageostrophic motions are growing very intensely. Okay, And here is again the illustration that there is a emission of inertial gravity waves. Here for your orientation are the this Hofmann diagram, time, space, and here is the phase velocity of baroclinic inertial gravity waves, barotropic inertial gravity waves, and you see that you are emitting constantly the baroclinic inertial gravity waves from this instability out.
How you construct it? Did you made a high frequency filtering or something?
Yeah.
Or yeah. It's not total, right? Yes.
And with the divergence field.
You're looking at
Because the proxy for gravity waves is divergent. That's just for comparison the saturation of the standard barotropic instability. Again, same variables. You see very few of hyperbolicity loss stuff. Okay, but you also see this ageostrophic barotropic instability, the second unstable mode. You also see the formation of small-scale structures. But in what concerns the hyperbolicity loss, it's totally different. It's lost at some moment, and then it recovers, and nothing else happens. So again, in terms of our physical interpretation, this means that that baroclinic ageostrophic inertial instability is constantly producing strong shears. This is hyperbolicity, which is maintained, and here it is transitory, and then you come back to normality in some sense. And here is the energetical saturation, and you see that it's completely different, because here there's kinetic energy which is growing, potential energy which is decreasing, in a completely standard scenario, although it is ageostrophic. And it's opposite to the energetics of what I showed before. There are some curious oscillations. I'll come back to that on the equator later, because there are some nonlinear oscillations superimposed on this spectrum jet. Okay, and again, the ageostrophic motions are intensified. Okay, so it's just to show you the comparison with standard baroclinic instability, but okay, I have no time to comment on that. So a summary of this first part, which was intended to to show you the basic ideas. We started 10 minutes later. Is that the leading long wave instability is asymmetric inertial and not symmetric one. It is dipolar baroclinic, localized at anticyclonic site, and symmetric one also exists, but it is dominated by asymmetric. Okay. That's the details. I'll skip them. So now we go to the equator. On the equator, the inertial instability is most natural. Zonal jets are ubiquitous at the equator, both in the atmosphere and the ocean, and their instability, surprisingly, at least I didn't find a lot, are not systematically studied. Again, the linear resonances of waves may be considered a source of instabilities, and there's a whole zoo of waves on the equator, so it is interesting to look at it. Again, this is the same system. Notation is a bit different because taken from another paper, but the same system written for two layers. The only difference is rho I replaces R. It is one for one layer and rho for another one. Two layers, momentum and mass equations. The only difference is instead of constant F, you have equatorial beta Y. And that's it.
Question.
Yes?
How did you do? Are you going to show beta plane two-layer shallow water?
Yes.
Numerical simulation?
Yes?
How did you deal with the caustic?
With what?
With caustic problem?
You'll see.
That's interesting.
Okay, so the only thing is that we change a bit our configuration, because we took here something similar to the Bickley jet, but it's just a Gaussian jet. Again, it's barotropic in a sense that velocity is the same in both layers. Okay, and the geopotential is adjusted in order to have a balanced state, meaning the exact solution of this.
So suppose your density increase continuously, will the answer would be basically the same, or will be seriously different? Instead of two layers, to have continuous function.
No. I'm still in two layers here.
Okay.
If I have time, I'll show you a continuous function later on. But I'll try to accelerate if you don't mind. So again, there are a lot of parameters, and you may play with them. This configuration which we are talking about, the equator is here. Now it is really a zonal jet. Cross-jet direction is meridional with y. And here is the sort of geostrophic jet, and here is ageostrophic jet. And the difference is that here you have the anomaly of absolute vorticity, which was explained in Junichi talk yesterday, which is never negative, and here it is negative. And so here at the fixed Berger number, you have a very slow jet, and here you have a very energetic jet. Okay. So here is, don't pay attention to this index M, because M means modified, and the background jet, basically on the equator, you have the potential vorticity, the state of rest, which is a linear function, and the jet modifies it, it depends, and it may create additional gradients of potential vorticity if it's strong enough, so the wave spectrum may be modified, but for today, you just forget the subscript M. R is Rossby waves. These guys are Poincare waves. You have two species of each wave, barotropic, baroclinic, because in two-layer model you have both, and barotropic are faster as usual. You have Rossby waves stuck to the zero with slow Rossby waves, and you have some news. You have Kelvin waves, baroclinic and barotropic again, propagating in the system, and this is a new thing, but they will be not important for our business. And here is the zoom of this part of the flow with dispersive Rossby and Yanai wave. Yanai is what was called mixed Rossby gravity in Junichi talk. It is something which interpolates between gravity waves if moving in one direction and Rossby waves if moving in another direction. So this is just to show you that in the stable configuration with a very low intensity jet, you have a whole zoo of waves, and here are the Yanai waves, which will be very important in what follows. They are dipolar in the cross-equator direction. Here is the barotropic one, here is the baroclinic one, again this geopotential anomaly and velocity field, and I'm showing them because they will be responsible for the main instability in this flow. You can show through the Ripa's stability criterion, which is a general sufficient condition for two-layer flows, or multi-layer flows in general, on the beta plane, that the instability threshold is Rossby 0.25. Okay, and here we are just above the threshold, and you see that strangely enough, strangely, the difference with the F plane is that still you're well separated from zero. This is normalized wave number, and the mean instability is not a resonance of Rossby waves as would be naively expected from the theory of barotropic and baroclinic instability, but the Yanai wave resonance. And there are two of them, barotropic and baroclinic, with very close eigen frequencies. This reversed with respect to the figures in the previous section. This is imaginary part, this is growth rate, and this is the phase diagram. It's just to show you that it is very difficult to disentangle. As is well known, the intersection between the dispersion curves is a proxy for instabilities, and as there are a huge amount of waves here, it gives you just an example of different resonances which may happen here, and there's a huge work to just disentangle all this. But anyway, you can forget this and see only growth rates, and you see that the leading instability is not due to the Rossby waves resonance, but due to the Yanai wave resonance, and is well separated from zero. Okay. Now, what happens when you increase Rossby number? But not drastically increase like in the previous F-plane example. You go through 0.5, 0.7, if I'm not mistaken, 1.2, 1.5. And this evolution of the growth rates only. You see a lot of mass because, as I explained to you, there's a huge amount of resonances, many instabilities, but we are interested only in the highest growth rates and leading instabilities. And here is these two Yanai wave resonances, baroclinic and barotropic, and what happens when you increase Rossby number? They move towards zero, And at some moment, between 1.2 and 1.3, you have a bifurcation and the appearance of the symmetric inertial line of anticipating instability. This curve is very similar. These two curves for the two leading instabilities are very similar to what we've seen in the F-plane. Okay, but the same bifurcation happening, and this is the standard symmetric instability you find in textbooks. And again, this is not dominant. The dominant one is here. There is again an instability swap for some wave number. Okay, and so the story goes in a very similar way as in the F-plane in this sense. Now this is a phase portrait of the most unstable mode. Okay, it's dipolar across the stuff. This is why it is Yanai-like, but it is not very easy to say because Yanai wave has a clear signature of the cross-equator velocity. Here you can see this cross-equator velocity, but it is not that clear, but still we identify as Yanai wave. That is why I'm saying modify Yanai, but it is not very clean. And it is clearly Baraclinic because this is what's going on with the same values represented for the geopotential anomaly and velocity. What's going on in the upper layer and the lower layer. The signature in pressure in the lower layer is much smaller. Okay, so the linear stability, I will not repeat what I already said. It's just that Yanai wave is responsible for this Yanai wave resonance. Dipolar structure across the equator is responsible for the leading instability, and the leading instability is at small but not zero wave number, and symmetric instability exists and belongs to the same family. That's the thing that I forgot to say in the first part. The fact is that this answer to one of the questions I asked at the very beginning, the inertial instability, the symmetric inertial instability is not alone, it's not standing alone. It belongs to a family. It belongs to this curve of essentially ageostrophic Baraclinic instability. Okay, and this is the limit, a long wave limit of this instability, although it is not dominant, at least for this stratification. So, I'm not showing you a lot of numerical simulations just to convince James that we see nothing extraordinary here. We see the formation of the vortex structures in the upper layer. In the lower layer, it is a lot of mass. Again, the relative vorticity is in the lower layer is evolving in this way, again forming sort of vortex-like structures and then dissipating. The energetics is interesting because, again, and even more clearly, we see here the transformation of kinetic energy into potential energy.
You're lucky your flow is not going out of the boundary. That's why.
No.
Okay, now I got you.
We are not on the sphere. We are on the beta plane.
Yeah, normally you should.
But we have these beta rails, which. But look at this. This is even more clear than in the previous example. You have this transfer of energy from kinetic to potential energy, mostly. And on top of it, you have this strange oscillation, which is not a numerical artifact, because of course we are doubling resolution routinely to see the numerical doubling and even more to see the numerical convergence. And this is not an artifact. This is some nonlinear oscillation in some long time. This is the typical equatorial time scale, as you see. And these are long time nonlinear oscillations superimposed on this flow after all. We don't understand their nature, to tell you the truth. Okay, now, I'm showing you the vertical shear. Again, the gray zones are here, and again, the hyperbolicity is lost, but well under control. And again, as I'm running out of time, I will not repeat the basic results. You can read them on the equator. But what's important, we have basically the same picture. We have the symmetric inertial instability, which belongs to a family, and it is not the most vigorous instability. It is his cousin with small but non-zero wave number, which is dominant. Okay, now in last 15 minutes left. So, but I started at 11:12. You don't want to hear it, I will stop here. No problem. But I think that's important, at least the linear stability stuff. Again, our motivation, this is real with capital R. These are primitive equations. Okay, and our motivation is maybe what we see, this dominance of the asymmetric inertial instability is just an artifact of this very crude stratification, very crude vertical resolution, because you can look at the two-layer model as a poor man or poorest man vertical resolution. Okay, you need baroclinicity, as I explained at the very beginning, to realize this instability. But the minimal thing is two layers. Okay, now whether what we see is the artifact of two layers or it is general. I'm saying, telling you the answer. The answer is it is general, but because to start this, there is a sort of a theorem established by Stephen Griffiths that, although in the tangents and it's just pure shear flow, but it doesn't matter, that the strongest instability in the limit of infinite vertical wave number is the symmetric inertial. How all this combines with this result? I'll show you the answer. And by anticipation, I can tell you that to get these Griffiths asymptotics, you have to have enormous vertical wave numbers. But in the very wide range of vertical wave numbers, you still have what I showed you in two layers. Okay, so again, this will be linear stability analysis plus nonlinear simulations. Our model are primitive equations. They are written here for the atmosphere. There is vertical diffusivity and dissipation introduced for the purpose of numerical simulation. Of course, for the study of linear stability, you don't need them, or you can use them. It's up to you. And what we'll be doing, we'll be working with, again, with the for the linear stability analysis, barotropic Bickley jet, on the background of the constant stratification, constant Brent-Weisel frequency. And what we'll be doing, of course, in the here is the profile of the barotropic Bickley jet. We are back to the F-plane, our first part. And there are, again, some standard parameters. And again, from the necessary condition for inertial instability, you have the threshold for the Rossby number where it can manifest itself. So that's it. Again, you have Rossby number, you have Burger number, which is now a baroclinic Burger number. For the linear stability, I'll come to this back for the WRF simulations. For the linear stability analysis, we have a periodic domain.
Periodic impact.
Sorry?
No.
I have no boundary. For the linear stability analysis, I'm just coming to that.
In vertical direction.
In vertical direction, I have modes. That's
vertically periodic.
Vertically periodic, yes. That's for technical reasons. For technical reasons. That's the profile of the flow. This is the geopotential anomaly. This is this flow again with the, if this anticyclonic shear is strong enough, you have conditions for inertial instability. And here is the potential vorticity, which may be negative. And here is the example for Rossby number 2.
It's vertically periodic for the perturbation.
For the perturbation, yes, of course. Yeah. I'm coming to that. So how we are doing that? We linearize, the background flow is just as it is. It is vertically homogeneous. You separate the problem and you're introducing the vertical modes, okay? And basically it is much more work, but for each mode you have something we've done for two-layer flow, okay? So you just repeat it for each M and go and go and go. It's a lot of work done by Bruno Ripstein, but it is done. Anyway, as a net result, we have the stability diagrams. And here is, again, it's a benchmark, or maybe considered as such, the stability diagram for small Rossby numbers. And again, what we have here, we have several vertical modes. You see M1, the gravest. By technical reasons, we don't go to M0. We have no true barotropic mode. We have the gravest baroclinic mode here, with non-dimensional vertical wave number 1, and we have two modes two different meridional modes for vertical wave number num, one and some representative of higher vertical wave numbers. This is just to tell you that this is a classical barotropic instability. This is the second mode of this instability, dipolar in this direction, and this is Baroclinic. Okay, again, this is a benchmark. That's what you expect. You recover the same butterfly mode for the dominant instability, this horizontal section of the mode, and this is the second barotropic mode. So everything as expected, barotropic instability is the strongest. And now again, I throw you the result of the linear stability analysis for Rosman number 2, the jet which was represented before. It's not everything is shown because there are many things here, but you have several curves for the growth rates for the increasing vertical wave numbers. And you see indeed, at least for those wave numbers presented, that you have the strongest instability is for highest represented wave number. We've gone much higher. But here, starting from some vertical wave number, you see the legend here, you again have this bifurcation and the appearance of non-zero growth rate at the zero wave number. And you have still the same stuff. You have still this symmetric inertial instability, because it is nothing like, as it is precisely it, is less strong than its asymmetric counterpart. Now, I am not showing this here. Indeed, if you go for very high, several, almost 1,000 here, you do make this curve flatter. It's flattening, and the symmetric instability becomes dominant. So there is no contradiction with Griffith's result, but there is a sort of a detail that you may not see it if you have not enough vertical resolution. The conclusion from this part is that vertical resolution is crucial, because you may have qualitatively different result if your vertical resolution is not sufficient. If you have no access to higher wave numbers, you impose the white noise on your jet, you will see structures due to this instability. If you have access to very high wave numbers, you will see more or less symmetric noise resulting or breaking resulting from symmetric instability.
What's the relevant dimensions parameter for M to say it's large? I mean, what do you compare?
It is, that's a good question. I don't remember it. Of course, it's always normalized in terms of the characteristic scale of the jet. It's L. The width of the jet.
Oh, so the viscosity must.
Yeah, but if you switch on viscosity, it will kill this highest stuff. Yeah, thank you. That's a useful remark. But anyway, so what we confirm here, that all we have seen in two-layer model, the poorest man vertical resolution, is valid for a very wide range of vertical wave numbers. Although there is no contradictions, and at very high vertical wave numbers, you do have the dominance of the symmetric instability. Yeah.
If you apply it to an oceanographic or atmospheric case, is dissipation an already relevant friction?
Is dissipation? Yes.
Continuing the remark that the higher order wave numbers will be.
Yes, but if I remember correctly, the Griffiths result is also valid when dissipation goes to zero at the same time. There's a triple limit in his result, which is analytical. But here, there is no dissipation in this stuff. And the dissipation will dump things. And basically, it will dump higher vertical.
But I'm basically asking, would the growing instabilities for high wave numbers saturate non-linearly, or would
you'll see the example if you allow me to show the results of Worf resolution. You'll see how it happens. Okay. But I just show you the horizontal slice of the model, and you see a striking resemblance of the most unstable mode with what we have seen in two-layer model. Okay. Now, Worf is much more realistic. Just I have 2 minutes. I'll I'll stop there. WRF is much more realistic in the sense that it is a real-life model. So you don't have infinite domain. You need to have a top boundary. So you need to render your jet more realistic. So we are just regularizing it. Okay, so it's real jet in the vertical too, due to this factor. But in its center, it has the same structure as our Bickley jet before. So there's a big chunk of the domain where it is like barotropic jet, and then it goes down. Okay, so in this way,
rigid with top and bottom.
Sorry?
It's rigid.
It's not rigid. In WRF, it is a real atmospheric model. It is just free pressure upper boundary.
So
And we have a rigid bottom. We have no topography. Yeah.
yeah, and you have realistic theta so far.
Yeah. So this is the background jet. You see, the stratification and velocity field, and here is the vertical vorticity in the jet. And again, if you have this vorticity very strong, you may have inertial instability. And we initialize this not with the most unstable mode, because with WRF it is much more difficult. We initialize it with white noise for the vertical velocity superimposed to the jet. And what you see is that basically this evolution, the norms of several first Fourier modes along the jet of the perturbation. And you see that the symmetric mode grows very fast, this really symmetric inertial instability, and then sort of slows down, and barotropic and baroclinic modes just catch it after that and become more vigorous after that. So basically, that's the evolution of vorticity in the cross-flow direction. And you see this homogenization of the anticyclonic vorticity, which is what you expect from the saturation of the inertial instability. It happens as it is. Time is in days because it's a real-life model. And this is the along flow view of the vorticity. This is initial perturbation. And you see that it sort of mixes up this anticyclonic part of the region, and then the standard barotropic or the gravest baroclinic instability takes over and forms these jets. Okay, so
Sorry, was that with beta or without beta?
it was on the F plane.
But on that.
Okay, so I skip this and come to the overall conclusions. So, as I said, asymmetric inertial instability is dominant in the large range of vertical wave numbers. It's saturated in a way like it is known for symmetric inertial instability by massively producing overturning motions and enhanced dissipation. And very high wave numbers are needed really to achieve the dominance of the symmetric inertial instability. And as in the last simulation, we've seen that it may evolve simultaneously. This is competition of the instabilities, if you wish, with the barotropic or baroclinic instability. And that's it. So the last remark, I already done it. It is that changing vertical resolution may lead to drastic consequences. And what's perhaps also interesting for oceanographers, the close relative of the inertial instability is centrifugal instability. And now this is work in progress, but it's almost finished. It will be submitted very soon with Noel Lahai, another student of mine. We carried out the same program for two-layer centrifugal instability with basically the same results. So the asymmetric modes are dominant in a large range of wave numbers. Finally, I didn't acknowledge or briefly acknowledge my collaborators. They are Bruno Ripstein, I didn't mention, I think, François Bouchou, with whom we are working on numerical realization of that. That's a terrible mistake. Here. Sorry for that. Lugan is here, Bouchou is here. Sorry. So this is published, this 2-layer. This is with Francois Bouchou, and this is with Raoul Pluganman, excuse me. Just noticed that. So this is the 2-layer stuff which is published a couple of years ago. This is a continuously certified stuff. I don't know what happens with it because 6 months passed after more or less favorable reviews and revision, nothing happens, which is very unfortunate for Bruno Epstein, who is applying for positions. And this one was submitted now, it's under revision 2. It's on the equator with unsufficient here. So sorry, you should interchange about Plugan there and Francois Bouchou here. Excuse me. So that's it. Thank you for your attention.
Suppose that the density constant is upper level and monotonic increase in the low level. So we have additionally brand versatile frequency in the low level. How this will affect the analysis quantitatively?
I said in the very beginning that I am choosing constantly, as you've seen, the barotropic configuration, barotropic jets. Whatever the stratification. For the barotropic jet configuration, it's easier to get inertial instability. Although, for baroclinic, really baroclinic jet, you may do it too, for more or less realistic atmospheric jet, etc. But you will need even higher Rossby numbers to get it cleanly. Okay. Now, if you change the stratification, as you see, if you have constant Bragg-Weissler frequency and zero Bragg-Weissler frequency in the thermocline or whatever, first of all, you need to have a rather intense jet. The answer is I don't know precisely, but there is no reason why the mechanism doesn't work. I mean, the only thing is that the setup of this instability may be postponed by the details of stratification, but I have no general rule relating the critical value of the Rossby number and the details of stratification. Moreover, I didn't say that. The general wisdom says that you need to have negative potential in the northern hemisphere, negative potential vorticity to get it. But not immediately after you cross the threshold of negative potential vorticity, you get it. You get it after some space. So there are details that are not elaborated yet. But again, my answer is that generally there is no reason that there will be no, that the same thing would not happen with the same consequences, but the details, the onset may depend on the stratification.
You understand that the problem is not solved at the moment, yes? It's open.
If you, this problem, if you wish, is not solved.
These are quite long wavelength modes along the jets.
Yes.
So if you take a realistic jet width, what scale do you get for the scale of the fastest growing perturbation?
Yeah, this is a good question. I didn't.
For example.
Yeah, I'll come back for some of these examples. Let's say, what you wish, equatorial or latitude?
Oh,
Whatever.
doesn't matter.
Okay, I'm here. So you see, first of all, the scale here is the width of the jet, right?
Okay.
The scale we're using is the width of the jet, and the wave number here is normalized with this width, okay, which is natural. And now this is stable. So in this scaling, for instance, for weakly unstable flow, just beyond the threshold of the instability, you have 0.3. That's long. For more, let's say, yeah. So these are small guys. There's a very long. So in fact, it is not that far from symmetric instability.
Yeah.
That's
Right.
what you ask.
So if you did it on a sphere, you might still see the m equals 0 mode.
Maybe.
Yeah.
Again, if you have discrete horizontal wave numbers, again, you may have your maximum sitting in between, so you have no access to that.
So, some further questions? Then let's thank the speaker again.
Thank you.